Great, thanks a lot. Okay, so I'll start by showing you a picture of an example of what algorithm design looked like in 1955. And what this is a map of the Soviet railway system at the time. Okay, and so it turns out that one of the earliest applications of theoretical computer science was when the CIA asked computer scientists to find a min cut in this graph. And to the best of my knowledge, they were able to do this. And also to the best of my knowledge, the CIA did not act on this information. Okay. So moving forward to 2014, this is a graph of what a more typical algorithm design problem will look like today. And this is a graph of all autonomous systems in the internet. And algorithms are run on this graph every second in order to route our internet traffic. Okay, so what's the difference between algorithm design 60 years ago and algorithm design today? So one thing you'll notice is that this graph on the left has much fewer nodes than the graph on the right. So obviously our algorithms today, they need to be much better and they need to run a lot faster. But that's not the aspect that I want to focus on in this talk. And instead, the aspect that I want to focus on is that in the graph on the left, there is one central authority that controls all the nodes and edges. The nodes have no interests of their own, and in this sense, they will just obey this central authority. Okay, in this graph on the right, there are 42,000 autonomous systems that control the nodes and edges. So they have their own interests, and they're going to behave in their best interest. Okay, so now I want to give you an example to show you that this is a real problem. So in 2008, there was a faulty BGP table update that caused a worldwide outage of YouTube. And what happened was that at the time, there was offensive material on YouTube that prompted the country of Pakistan to want to censor it. So they asked their ISPs to update their BGP tables to map from YouTube to nowhere instead of correctly to YouTube. And just because of the way that BGP worked at the time, this was inadvertently broadcast to the rest of the world and caused YouTube to be shut down for several hours. Okay, so what's the point? So here's a quote that I think summarizes what happened nicely, which is that nobody ran any viruses or worms or malicious code. This is just the way the internet works. Okay, so the point is that Pakistan was not trying to shut down YouTube for the entire world. They were just doing what was in their best interest, which was to shut down YouTube for them. And because of the way that BGP was set up, this caused the entire system to shut down. Okay. So now I want to put this into a more general context for you and talk about what we think of as traditional algorithm design. So in traditional algorithm design, we think of being given an input and being asked to produce an output. And then what happens in between is what we call the algorithm. Okay? And for many problems that we still face today, this is the right way to think of your problem. But as the example that I just gave you shows, sometimes there are other things we need to consider. Okay, so that example showed that one thing you need to sometimes consider is that maybe you don't have the input, but you learn the input from strategic agents, and these agents may lie to you if they think it will help them. Okay, this is just one example though. Another reason is maybe you don't know the entire input because you're trying to make decisions today about the future with limited information that you have. Another example is maybe it's just not possible to have an algorithm that works for every possible input. So you need to settle for what we call like average case analysis. And as a last example, maybe it's just not good enough to solve the problem, but you need to solve the problem in a particularly simple way. Maybe this is because you want normal people to be able to interact with your algorithm and understand what's going on.
And this is not the point of your talk, but I can't help but noticing that it's only in a context like this that worst case solution impossible would be considered a bad thing.
Yeah. I guess, yeah. But so for the rest of the talk, I am going to be talking about average case analysis anyway. Yeah, but I did want to point out that, so for the rest of the talk, I'm going to focus on the strategic agents aspect, and I'm going to touch on each of the other three things at the end. But I just want you to think of algorithmic mechanism design as being part of this broader context, which is new challenges in algorithm design that we can't overcome by just doing traditional algorithm design better. If that makes sense. Okay, so we need new tools. Yes?
I can't help but notice that, especially the following, the next three, I know these aren't what you're focusing on. You say this is new, but artificial intelligence has been working on those three problems for decades. I'm just wondering, does your field...
Yeah, so I guess we should have been then, I guess, for a while, but we... But traditionally we don't. Yes, that's
so brilliantly too.
Yeah. Yeah. So I guess I would say that traditionally I don't think that average case analysis I think is not too new, but especially cases where like the algorithm has to be particularly simple, like that's for mathematical beauty, that's always desired, but it's never been like an explicit constraint, I think, in algorithm design. So yeah. Yeah, maybe we should have been for longer. Okay. So specifically, when I talk about algorithmic mechanism design and dealing with strategic agents, I want to think about settings where you don't know the input exactly, but you have to learn the input from strategic agents. Okay, so why is this interesting? This is interesting because the agents get some kind of payoff based on the output you choose. So imagine that maybe they know what algorithm you're going to run, and maybe they think they can gain something by lying to you about the input because it will cause you to choose an output that they like better. Okay. Oh, sorry. Whoops. And I did want to say one more thing. Okay. And in this setting, I'll call what happens here, instead of an algorithm, I'm just going to call it a mechanism. So that's just to introduce terminology to differentiate these two settings. Okay. So in a seminal paper of Nissan and Ronin's in '99, they introduced the following question, which is how much more difficult are optimization problems on strategic input versus honest input? So how much harder is mechanism design than algorithm design? And so the dream with respect to this problem would be to have some kind of black box reduction from mechanism to algorithm design that worked for any optimization problem. So here's what I mean in a picture, is that what we really want here is this mechanism that works on strategic input, and maybe all we have is an algorithm that works on honest input. And furthermore, when we say we have black box access to it, that means that all we can do is probe it with inputs and see what output it produces. And what we'd like to be able to do is to get this mechanism that we want by just probing this black box that we have over and over again. Okay? So why specifically do we want a black box reduction for this problem? So one reason is that so much more is known about traditional algorithms than mechanisms. So a very reasonable hope is that maybe we can reduce some of these hard unsolved problems in mechanism design to hard problems in algorithm design, but ones that we have already studied because we've been doing it for much longer. A second reason is that this would allow a much larger community to be able to tackle these important mechanism design problems because we'd enable progress by using purely algorithmic techniques. Okay? And last is we might hope that a reduction like this, in addition, would help us understand like what makes incentives so hard to deal with. So why does mechanism design seem to be more challenging than algorithm design? Okay, and so what I'm going to show you in this talk is that a reduction like this does exist as long as you put the right qualifications on what you want to get out of it.
Sorry, could you go one slide back?
Yes.
I didn't get that. So really what you want is this mechanism for the same algorithm that with a strategic input, and you're going to do that by playing with the black box?
Yes, that's correct.
The intuition bit?
So, so I guess I'll get to that later. The reason that you might hope that this is possible is that, you know, these two problems are similar in some sense, right? You're solving the same problem. The issue is just that for the mechanism, what we're trying to overcome is that we want to do this in a way that the agents won't want to lie to us about the input. And so maybe you can hope that if you're, you know, think of it like if you're really good at solving this algorithm design question, then maybe you can use this solution in a very clever way to, you know, solve it in a way that also encourages the agents to tell you their true input. So I don't know if that's a very strong intuition, but maybe throughout the talk you can get more. Yeah, sorry.
One other dumb question. Why do you have to treat the algorithm as a black box if you're the designer?
So, right, so it's better if you can treat it as a black box. The idea being that we would love to apply this over and over again. And if we have to, every time we want to apply it, look inside the algorithm and understand the structure of the algorithm, then that'll make it really hard every time we want to apply this reduction. We have to learn a lot about the specific algorithm we're using. Whereas we would love to just say, I don't care what it does, just probe it with input and see what output it gets. Does that, yeah. Okay. Okay, cool. So now I'm going to tell you formally about the problem we study. Okay, so in the problem setup, there's going to be a set of M agents who are responsible for reporting part of the input to you. And there's going to be a set of outcomes that you, the designer, are choosing from. Okay, so for now, I want to have these outcomes be completely abstract. So think of it as like one possibility is maybe we build a bridge, another possibility is we build a hospital, and a third possibility is maybe everyone here gets a bunch of bananas. Okay, so abstract. And the idea is that the agents have values for every possible outcome, and we'll say that their type stores that information. So you should think of their type as a function that takes as input an outcome and outputs how much they like it. Okay? I'm also going to use the term type profile throughout the talk, and a type profile just lists a type for every agent. Okay? Now there's one important assumption I'm going to make that is normal for mechanism design, which is that we're going to be in a Bayesian setting. And what that means is that the other agents in the designer, they have some prior information about what they believe the other agents' types are, but they don't know the type exactly. So think of it as everyone knows this distribution D, but no one knows exactly this type T. Okay. Now the designer's goal is to choose one of these outcomes, and the outcome that he chooses has to be in some sense feasible. Okay, and I'll give you examples shortly of what it might mean for an outcome to be feasible. In addition to choosing an outcome, he's also allowed to charge prices to the agents. Okay, and he wants to do this in a way that optimizes some objective function that he has in mind, that again I'm going to leave abstract for now, but I'll give you some examples shortly of what that might look like. Okay, so now let me tell you about the strategic aspect of the problem. So the first thing that's going to happen is a designer is going to design his mechanism, and a mechanism has two parts. There's an algorithmic component that takes as input a type profile and selects an outcome. And there's a payment component that takes as input a type profile and outputs how much each bidder has to pay. After he designs his mechanism, he asks the agents to report their types, and then he chooses whatever outcome and charges whatever prices he promised. Now every agent, based on the mechanism that they're playing, based on their own preferences, and based on whatever they believe the other agents are going to do, they're going to choose a type to report. And because they're strategic and not necessarily honest, they're going to choose the type that maximizes their own utility, which may or may not be their real type. Okay. So now subject to this agent behavior, the goal of the designer is to first come up with a truthful mechanism, and the specific notion of truthfulness we're going to study is called Bayesian incentive compatible. And that means that if every other agent is telling the truth, it's also in your interest to tell the truth. Okay. And then second, subject to being truthful, we want to find the mechanism that optimizes the designer's objective. Okay, so we're looking over all truthful mechanisms, find the one that optimizes the designer's objective. Okay, so now I know that everything I said so far has been pretty abstract, so I just want to give you a couple of examples to try and help ground this. Okay, so as one example, maybe you're a local government and you have funding to build a new school, and you're trying to decide if you should build like a generic school, a science school, or an art school. Okay. Now your feasibility constraints might be that you only have funding to build one school. And also, because it's a public school, as soon as you build it, any child who wants to has to be allowed to attend. Okay, so these might be what your feasibility constraints look like. Okay, and in this case, you want to maximize what's called welfare, which just sums over every child their happiness for the school that you choose to build. Okay, and again, the mechanism design challenge here is that you don't know beforehand how much each child likes the different options. Okay, so that's the mechanism design challenge that you need to overcome. As a second example, maybe you're trying to sell ad slots to advertisers, and this time you should not be giving the same slot to more than one agent, and you also should not be giving the same agent more than one slot. So you can think of these as your feasibility constraints that say that your solution has to be a matching. Okay? And this time you want to maximize your revenue, which just sums over every agent the amount that they pay you. And again, here the challenge is that a priori, you don't know how much each agent is willing to pay for each of the different slots. Okay. As a last example, maybe you have a bunch of computational tasks that you want to schedule on different machines. And this time, every job should be assigned to exactly one machine, but it's okay for the same machine to process multiple jobs. So think of these as your feasibility constraints. And this time you want to minimize what's called the make span, which is the processing time of the last machine to finish. So that would be the maximum over all machines of their processing time for the outcome that you choose. Okay, and again, the challenge here is that a priori you don't know the processing times. That's private information to the machines of how long it will take them to process each job. Okay. So now I want to tell you, using prior work, what's already known specifically for black box reductions about these three problems. Okay, so for welfare, the state of affairs is actually quite good. So there's a seminal series of papers by Vickery, Clark, and Groves that shows that if you have an optimal algorithm for welfare, you can turn that into an optimal mechanism for welfare. Okay? And their reduction is actually very simple, so I'm just going to show it to you. So the first thing that happens is every agent is asked to report a type. So here, this is my advisor Kostas. This is saying that his type, his value for the bridge is 2, his value for the hospital is 6, and his value for the bananas is 3. Okay? All of these types are then given as input to the optimal algorithm, and then the mechanism selects whatever the algorithm outputs. So in this case, the algorithm and the mechanism both choose to build the hospital because the total welfare of the hospital is 13. Okay? And so the technical work in proving that this is a good idea is that VCG showed that there exists a payment scheme that makes this entire process truthful. Okay. So something I want to point out is that this reduction does not work if this black box only solves a problem approximately. Okay, so if this black box doesn't solve the problem exactly, this entire reduction doesn't give you anything meaningful. But there was a recent series of papers by Hartline and Lucier, and Hartline, Kleinberg, and Malekian, and also Bay and Huang, that gave a more involved reduction that was able to accommodate approximation. One way in that the reduction is more involved is that it requires you to probe this algorithm over and over again on different inputs. So not just the input that you get by asking for their types. Okay. So now I'll tell you what's known for revenue. So the state of affairs for revenue is significantly worse than for welfare, but we do still at least know something. What we know is in a seminal paper of Meyerson's in 1981, he provided the revenue optimal auction for selling one item. Okay, and that auction is also simple, so I want to show you what it looks like. So it starts by asking every agent to make a bid. These bids are then transformed into virtual bids, and then the item goes to the highest virtual bidder. Okay, so I want to tell you a couple things about this approach. So first, I want to claim that you can view this as a reduction to welfare. So why do I say that? Because the apple is going to the highest virtual bidder. So I want to think of this as maximizing welfare on these virtual bids. Okay. Second, I want to point out that even though Kostas was the highest bidder, he was not the highest virtual bidder. And something else you notice, this is Yang, one of my co-authors, that even though he and I had the same bid, we got mapped to different virtual bids. Okay, so the only reason I'm saying this is because these things might seem counterintuitive, but they're an intended property of the reduction. And I also want to point out that Meyerson has a specific formula that he uses to generate virtual bids from bids. But I'm not going to give you details about it. Okay, so the next thing I want to say is that Meyerson's reduction does extend beyond single item settings to what are called single dimensional settings. So by that I mean if you have 2 copies of the same item for sale, then the second apple will just go to the second highest virtual bidder. But it doesn't extend to what are called additive or multi-dimensional settings. Okay, so if you're trying to sell an apple and an orange, then just using prior work, we have no idea how to sell apples and oranges together. Okay, so now let me tell you, just to recap in a chart, what I've told you so far. So we said for welfare, the state of affairs is quite good, and that if you want to truthfully optimize welfare, you just need to be able to algorithmically optimize welfare. For revenue, we said we still know something. In single-dimensional settings, if you want to truthfully optimize revenue, you need to be able to algorithmically optimize welfare. Okay, but we don't know what to do in additive settings or beyond additive settings for revenue. And for objectives like minimizing makespan beyond revenue, we really don't know a lot. Okay? In fact, the only thing we do know is an impossibility result that says there is no black box reduction from minimizing makespan truthfully to minimizing makespan algorithmically. Okay, and that was a recent result by Chalo and Morlica and Lucier. Okay, so what I'm going to show you in this talk is first that this reduction from revenue to welfare extends beyond single-dimensional settings to additive and more general. And second, I'm going to show you how to get around this impossibility result by changing the algorithmic objective to that same objective plus welfare. And I'll tell you what I mean by that on the next slide. Okay, so our main result is a polytime reduction from mechanism design for any objective to algorithm design for that same objective plus welfare. Okay, so in a picture, here's what I mean. The mechanism is going to start by asking agents to report their types. These types are going to be transformed into virtual types, And this process has nothing to do with the specific formula that Meyerson used in his reduction. And then all of these types and virtual types are going to be plugged into an algorithm. This algorithm is going to try to find the outcome that optimizes O when computed with respect to the real types, plus welfare when computed with respect to the virtual types. Okay? And then whatever this algorithm outputs, that's what the mechanism will choose as well. Okay. So I want to tell you about this reduction, that it is approximation preserving. So that means that even if this black box can only approximately solve the algorithmic problem, what you get in the end is an approximately optimal truthful mechanism. And second, there are no constraints on the types for which the reduction works. So these types don't have to be single dimensional or even additive. They can be whatever you want. Okay? So here's a quote that I like to give about describing what this reduction says. What it says is that transitioning from honest to strategic input computationally is no more difficult than adding welfare to your objective. Okay? So just to be clear, what I am not claiming is that because of this reduction, we now know how to solve every mechanism design problem that we want. But what I am claiming is that now we have an algorithmic framework to tackle them that we didn't have before. Okay, so now I want to give you 3 examples where we are able to actually design this black box and to make progress on important problems that we weren't able to do before. Okay, so the first example is this problem that I mentioned earlier called multidimensional mechanism design. So just to remind you, this is where you're trying to sell apples and oranges together. Okay, and to remind you, Meyerson's seminal paper shows that in single-dimensional settings, the revenue optimal auction is a welfare maximizer on virtual bids. And since then, a major open question has been, what does a revenue optimal auction look like beyond single-dimensional settings? And so as a corollary of our main result, what I'm going to show you in this talk is that in additive settings, the revenue optimal auction is a distribution over welfare maximizers, and you can find it in polytime. So what do I mean by that? I mean that the optimal auction randomly maps types to virtual types, and this has nothing to do with Meyerson's formula, and then it maximizes welfare on whatever these virtual types happen to be. Okay? And also for this specific setting, maximizing welfare is easy. You just give every item to the highest virtual bidder. So that's what I mean by you can do it in polytime. Yes?
So you mean in polytime for the exact set of bidders that you have this time?
Yeah, so what I mean is polytime in the size of the distributions that you take as input.
So the number of types?
The number of types for one bidder. Right, so it's not polynomial in the size of the joint type space of all bidders together, but it is polynomial in the size of a single bidder's type space. Yeah, thanks. Okay. So the second application, so you remember I said this problem of make-span minimization is where you have a bunch of jobs that you need to schedule on machines. And specifically, we want to talk about unrelated machines. And what that means is that the processing time of job I on machine J has nothing to do with processing the same job on a different machine or a different job on the same machine. Okay, and so this was the original problem that was studied in Nissan and Ronin's seminal paper. And in this talk, our main result is going to show that this mechanism design problem reduces to algorithm design for minimizing make-span plus welfare. Okay, now it turns out that this problem is NP hard to approximate within any finite factor. So not just a constant factor, a finite factor. So that means that we have to do more work in order to design this black box that we're going to use. And so what we're able to show is that we can extend this reduction to accommodate a certain kind of bicriterion approximation. And what's even more cool is that this specific kind of bicriterion approximation was developed 21 years ago by Schmois and Tardosh. Okay, so as a corollary, this gives us a polytime to approximate mechanism for make-span minimization on unrelated machines. Okay, so if you don't care about the specific result, what I want to highlight is that what happened with this reduction is that we were able to take algorithmic techniques from pure algorithm design, where we're very comfortable coming up with like complex algorithms, and use it to solve a mechanism design problem. And in mechanism design, there's actually not a lot of precedent for designing very complex truthful mechanisms. Okay, so the idea is that this reduction allows us to use techniques that we're comfortable with from pure algorithm design and solve a mechanism design problem. Okay, as a last example, maybe we care about beyond multidimensional settings, we still want to maximize revenue. Okay, so our reduction says that all you need to do is maximize welfare on these virtual types, but it turns out that this is often an NP-hard problem to solve. Okay, so how do we cope with this? Well, we showed that for revenue, our reduction actually holds both ways. What I mean by that is that if you had a truthful mechanism that could maximize revenue, that would imply an algorithm that could maximize welfare for any virtual types. Okay, so as a fuzzy corollary of this, this says that for this specific setting, maximizing welfare is the right computational approach to try and maximize revenue because you can't avoid doing it. And something else we're able to show is that by this reduction, we now know that it's NP hard to truthfully approximate revenue within any polynomial factor for even one submodular bidder. And submodular just means that as you get more and more items, you have diminishing marginal returns. Okay, so again, even if the specific result is maybe not exciting to you, what happened here is that we know how to prove hardness of approximation in pure algorithm design. We're very comfortable doing that. But in mechanism design, there is not a strong precedent of being able to prove hardness of approximation for revenue maximization. Okay, so this reduction let us use techniques that we're comfortable with to solve mechanism design problems.
This might be an artifact of your illustration where you had your advisor bid 10 and the other, I think both of you bid 8, and then you made these what appeared to be random numbers here for the virtual type. And so it would seem like, from a naive outsider's point of view, that all the magic comes in the mapping from your bids to the virtual types.
Yes, that's definitely true.
Are you going to talk about that?
So I'm not going to talk about how we generate the mapping. You'll see a little bit of it, and if you still have questions, I can tell you more detail after. But you will see a little bit of where the mapping comes from. But for the most part, I would say we don't know a lot of structure about this mapping, and the reason it seemed random to you is because that's the extent of the structure we know about it at this point, which is not a lot.
If that's the case, then I guess the follow-on question would be, anything you prove on virtual types, if you don't have a good mapping back to actual bids.
So we do know enough about the structure that that it is meaningful to go from types to virtual types, but we know nowhere near as much structure as we do for like Meyerson single-dimensional settings. But maybe
we can talk.
Yeah, that sounds good. Okay, so now I want to tell you just some tools and techniques that we develop in order to prove this reduction. And for now, I want to keep things simple. So the objective is going to be revenue. The agents are going to be additive. And to remind you what that means, there are n items, and each agent has a value for each item. And their value for a set of items sums their value for every item in that set. Okay, so here's what the proof overview is going to look like. So the first thing I'm going to do is we're going to write a linear program that's going to solve the problem we care about. Now the good news is that it is going to actually solve the problem. The bad news is that it's going to be a really enormous linear program. So it's going to have way too many variables for us to have any hope of actually solving it. Okay, so what we're going to do is we're going to describe mechanisms in a more concise way that will let us reduce the number of variables, and then that'll let us write a concise linear program. Okay. Now the second step is we have to actually solve this linear program, and the reason that this is actually challenging is because when we move to a concise description, we can no longer write down explicitly the linear constraints that we have to satisfy. So we need to use non-trivial techniques. So what we're going to do is we're going to develop some new convex optimization tools, and that's going to show that if you can have black box access to this algorithm for O plus welfare, with these new tools you can solve this linear program, and that will give you a concise description of the optimal mechanism. Okay, now the last step, and this is I guess loosely related to what you were saying, is that just because you have a description of the optimal mechanism, that doesn't mean that you're done. You need to actually run the mechanism. So you need to be able to, when people show up and tell you their types, you have to choose an outcome and you have to charge them prices. Okay, so the last step is we're going to prove a structural theorem that says that if you give me a concise description of a mechanism, then I can tell you how to implement it. Okay, so all three of these steps together is going to prove the main result. And I'm going to start by telling you about this linear program. Okay, so the first thing we want to look at is how do you describe a mechanism? So I told you earlier that a mechanism is just a function. So one way to describe a function is you just list for every possible input, what's the output? Okay, and now that we're just describing mechanisms as a long list, we can think of them as just a large dimensional vector. Okay, And if we're thinking of mechanisms as vectors, it makes sense to ask the question, can we write some kind of program to optimize over the space of truthful mechanisms? And the answer is sure, and I'll show you how to do that on the next slide. But really what this is going to look like is it's going to look like a program that optimizes over the space of all algorithms plus some linear constraints to encourage truthfulness. Okay, so here's what that linear program looks like. So it's going to have a variable for every possible input and for every possible outcome. What is the probability that that outcome gets chosen on this input? And for every possible input, what is the price that each agent pays? Okay, so we need the constraint that the mechanism is truthful and feasible. And these are linear constraints, but I'm not going to write them down. Excuse me, and we want to maximize our expected revenue, which is also a linear function, but I'm also not going to write it down. Okay, so one reason that I'm not writing it down is because I'm not advocating this as a good solution. Okay, so the problem is that this linear program is really enormous. It's enormous because there are way too many variables. So here I have a variable for every possible input, for every possible outcome. Okay, so that's way too much. Yeah?
Maybe I'm misunderstanding something here, but if the kinds of things that you're buying, selling are continuous quantities like money or oil, why is it that there's a finite number of, I mean, how can you even write that thing down?
Sure. So what I would say is that if that's the case, the right thing to do first is to just discretize everything. You can show that that will cause you to lose something, but you won't lose a lot by doing that. So let's say you round, like if it's oil, you round everything down to the gallon or something, and that will at least make it finite. And once it's finite, you can at least write this, but it will still be huge. So you will lose something by considering things that are not continuous but discretized, but you won't lose a whole lot. So think of it as like rounding. If you want to round very fine, then yeah. Okay. So the idea is that
you're going to set an operator where like this is the total amount of oil in the world, so we're going to.
Yes, yeah, something like that. Yeah. Okay. So the idea is that we want to be able to describe mechanisms in a better way than just this explicit function description. Okay, so what we're going to use is something called the reduced form. The idea is that we don't really need all of this information. We don't care about what happens on every single input. And so what we're going to store is just for every agent and for every item, what's the probability that they get that item when they report all their possible types? And for every agent, what's the expected price they pay when they report each of their possible types? Okay, so here's what I'm getting at, is that if you look at a mechanism is this very complex object, but that I, as an agent, I don't actually care about all this complexity, and I'm not even really capable of processing all this complexity. So really, when I look at a mechanism, all I see is this reduced form, which is the information I've stored here that's much simpler. Okay, and furthermore, what I mean is that if I look at two different mechanisms, maybe they're obviously different and they're both very complex. If they have the same reduced form, then to me they look the same, and I'm indifferent between them. Okay, so now that we're using reduced forms to describe mechanisms, we can think of a mechanism as a low-dimensional vector. And by low, I mean polynomial in the input size. And we want to say that a vector is feasible if it corresponds to an actual mechanism. Okay, so here's what I mean by that. I mean that here I have the space of all mechanisms, and here I have the space of all conceivable reduced forms. So by that I mean all vectors that at least have the right number of entries to possibly be a reduced form for a mechanism. Now every mechanism induces a reduced form, and the image of this map is what I'll call the feasible reduced forms. Okay? And so something that we can show is that the space of feasible reduced forms is at least convex, so there's some hope of running a linear program over this space. Okay?
So what are the assumptions that you can always get such reduced form? So for example, if you think the mechanism as a Turing machine computation, then...
So whether or not you can compute the reduced form efficiently is a good question. But every mechanism, these quantities definitely exist for every mechanism. So whether or not you can compute them efficiently is another question that we do have to address. But but without talking about computation yet, these quantities are always well defined for a mechanism, right? So I was going to say, so for any mechanism, when you run it, there is, for every agent, there is some probability that they get each item, right? Like that probability exists. Whether or not you can find it is a good question, though.
This is a simpler question. I mean, what's a reduced form that doesn't correspond the other way to a mechanism?
Sure. So let's say that we're in a single item setting, and I say my reduced form is that you get the item with probability 1, and I get the item with probability 1,
Okay.
and everyone here gets the item with probability 1. Right? Then you
Oh,
say,
it's for everybody,
yeah, right. You say that there's no mechanism that's going to give you that as its reduced form. Right? Yeah. Okay. So now that we have reduced forms, here's a linear program that we can write that's going to be smaller. Okay, so we're going to have variables for each component of the reduced form that I just talked about. So that's for every agent, for every item, for based on what type they report, what's the probability they get that item, and for every agent, what's the expected price they pay when they report different types. Okay, we need to constrain that the mechanism is truthful. Here's a linear constraint that does that. I'm not going to read it out loud, but I just wanted to put it up there to prove to you that it is in fact linear. And we still want to maximize your expected revenue, which is still a linear function. I'm also not going to read that one. Now the new challenge is guaranteeing that a mechanism is feasible, so guaranteeing that a reduced form actually corresponds to a mechanism. This is now a hard problem. Okay, and it's not one that we can solve with just a few linear constraints. So our new challenge is addressing this. Okay, so just to recap what we have so far, we have a succinct linear program, as in the number of variables is small, that will solve our problem. But what we need now is an algorithm that can tell us when a reduced form is feasible or not. Okay, so here's an example, and so this example is to help you understand first what does it mean for a reduced form to be feasible or not, and second, I want to convince you that this is an interesting algorithmic problem. Okay, so we're going to start in a simple setting. There's going to be one item, 2 bidders, and each bidder is going to have 3 types, and the feasibility constraints are that you can only give the item out once. Okay, so what this diagram means is that bidder 1 has 3 possible types, A, B, and C. He's each type with probability 1/3. And this means that whenever he says his type is A, he should get the item with probability 1. If he says B, he should get it with probability 1/2. If he says C, he should never get it. Okay, and now here's a reduced form, and we want to ask, is it feasible? Okay, so we can start trying to reason about this. And the first thing we'll do is we'll say, well, A is supposed to get the item with probability 1. So A needs to get the item always. If he's against D or E or F, A should always get the item. So we have to do this, but once we do this, at least we've satisfied A. Now that A is always getting the item when A and D show up, if we're possibly going to have pi of D equal to 2/3, D now has to beat B and C, always. Okay, so again, we have to do this, but once we do this, at least D is satisfied. And now, because C and F don't want the item at all, we may as well say, well, whenever B and F show up, we'll give the item to B. Whenever E and C show up, we'll give the item to E. And this gets both of their pi's up to 1/3. And now the last decision we have to make is what happens when B and E both show up. So in order to get pi of B up to 1/2, we would need to have B win with probability 1/2. And in order to get pi of E up to 5/9, E would need to win with probability 2/3. But I only have one item, so I can't give it to B with probability 1/2 and E with probability 2/3. So that means that this reduced form is infeasible. Okay, so what happened? So I want to say that that was actually a decent amount of work, and this was a very simple setting, right? So we had this nice starting point because pi of A was equal to 1. We only had 2 bidders, we only had one item, and we had no weird combinatorial constraints. Okay, so I want to say that we do need kind of like a more principled approach if we want to solve this problem in these harder scenarios. Okay, so the approach we're going to use is what's called the equivalence of separation and optimization. To tell you what that means, let me define what a separation oracle is. So a separation oracle for a convex region P takes as input a point X and outputs either yes, if X is in P, or a violated hyperplane otherwise. So let me give you a picture of what that means. So here's this convex region P. This black point is inside P. So when I run the separation oracle, it should say yes. This red point is not in P. So when I run the separation oracle, it should say no. And it should also output this hyperplane that separates the red point from the rest of P. Okay. So there's a famous theorem of Kachian that a lot of you have probably heard already, which is that if you have a separation oracle for a convex region, then you can optimize linear functions over that same region. Okay, and that's using what's called the ellipsoid algorithm. So for our context, what that means is we just need a separation oracle for the space of feasible reduced forms. Then we can solve our linear program. Okay? Now there's a less known theorem that says that actually the other direction is true too. If you can optimize linear functions over a convex region, then you can get a separation oracle for that same region as well. Okay? Now a good question to ask at this point is, okay, but who cares about the other direction? Like, who uses separation oracles for anything other than optimizing linear functions? Okay? So it turns out that one common usage is that maybe, and this is exactly the one that we're using, is that maybe you want to optimize a linear function over the intersection of two convex regions. And just being able to optimize functions over each region separately doesn't tell you anything about how to optimize over their intersection, unless you go through this reduction. Okay? And just a historical side note, this approach is actually what gave us the first polytime algorithm for submodular minimization. And there are other uses of separation oracles as well, and one of them is going to come up in a couple slides in the talk. Okay. So that's the second ingredient, is we have this equivalence of separation and optimization. It says all we need now is an algorithm that can optimize linear functions over the space of feasible reduced forms. Okay. So the last ingredient is a little bit technical, so I'm not going to go into details. But what we show is that if you have an algorithm that can optimize welfare, then you can optimize over the space of feasible reduced forms. Okay, so there are two steps to this. The first is we need to correctly interpret what does it mean to have a linear function in this space of feasible reduced forms. And second is, this is the more technical component, is we actually need to strengthen this equivalence of separation and optimization a little bit to accommodate a kind of sampling error. Okay, so I know that that doesn't tell you a lot about what's going on, but I did just want to give you a hint as to like the technical meat in proving this result. Okay, so now with these three ingredients, what that means is, let's say we start with an algorithm that can optimize welfare. We can plug it into ingredient 3 and get an algorithm that can optimize linear functions over feasible reduced forms. We can take this algorithm and plug it into ingredient 2, and that will give us a separation oracle for the space of feasible reduced forms. We can plug the separation oracle back into ingredient 1, and that will let us solve this linear program and find the revenue optimal reduced form. Okay?
Okay. Sorry, 2 questions.
Yep.
What constitutes sampling error in this world?
So think of it as I give you a mechanism and I want you to tell me its reduced form. An easy thing for you to do is you can just sample profiles and see who gets what items in this mechanism, and that will give you a decent approximation to what the reduced form is. And essentially that's what we do, and so we don't compute reduced forms exactly, we have sampling error, and that's what this comes from.
I see. So you mean the probabilities that come out will be biased?
Yeah.
With the skew of
Yeah, that's right. So they'll be close but not exact. Yeah.
As opposed to it lies to you at some point.
Yes. Yeah. That's right. Yeah. Okay. Sorry. And so just to recap, we said this is not. Oh, sorry. Yeah.
Yeah, okay. I think the key idea here is to use the reducer forms, right, which is polynomial to the input side.
Yes.
Then what about in some scenarios that you don't have such conditions? For example, if the benefits of each bidder is also depends on the benefits that other bidders get, which could be complex function of such input, then how do you handle that?
Yeah. So I would say, so then we can't use the reduced form. We need to describe mechanisms in a different way, but we can. So I wasn't planning on giving details about that, but there are different ways you can describe a mechanism in a concise way other than just the reduced form. And then you would, yeah, so I can tell you after specifically how you would do it for different settings.
Okay, because it looks like everything here are based on the reduced form.
Yes,
So,
so that's exactly right. So I would say the difference is that the skeleton is the same, but you start with a different kind of description. Yeah, so I can tell you what the description looks like after.
Okay.
Okay. So again, just remember that we said the story doesn't stop here. It's not enough just to find a reduced form. You need to actually implement the mechanism. Right? So that's the last step. And just to remind you, this means that we need to be able to take as input a type profile and select an outcome and charge prices. Okay? So what we do on this front is we prove, this is our structural theorem that says that if you give me any reduced form that is a corner of the feasible region, then this reduced form can be implemented by maximizing welfare on every profile. So what I mean by that is that every corner changes the input in a different way, so generates their virtual types in a different way, but then just maximizes welfare for these virtual types. Okay? And then second, this other use of separation oracles that I hinted at before is that if you give me a separation oracle for a convex region, I can decompose any point in that region into a convex combination of corners. Okay, so here's how we implement the mechanism we get in the end. So here's this, let's say this orange reduced form. This is the one you want to implement. So the first step is we write it as a convex combination of the red reduced form plus the yellow one plus the black one. And we can do this because we have a separation oracle. We sample a corner with the right probability. So let's say we sample the red one. Now we generate virtual types according to the red corner. And then we implement the red corner by just maximizing welfare on these virtual types. Okay? Yep.
What's your guarantee that corners exist?
So you're asking what if it's not what if the boundary is not, doesn't have like these points? So I'd say, so by corner I just mean any extreme point. So if it was like a circle, then so if the convex region looked like a circle, then it would be any point on the circle. So I mean extreme points, any point that doesn't lie on a, so let me say, so any point, not these, but the corners are okay, or if the boundary is smooth, any point on the corner. So think about it like the true extreme points, the non-degenerate extreme points. Yeah. Okay, so this was the last ingredient. And now with everything together, this proves that you can find and implement a mechanism that optimizes revenue for additive bidders in poly time as long as you have black box access to an optimal algorithm for welfare. Okay. So that already is a pretty cool theorem, but I did promise you something more general earlier, which was that this theorem would be approximation preserving. It would work for arbitrary agents that weren't necessarily additive, and that it would work for arbitrary objectives that weren't necessarily revenue. Okay, and so the reason that I chose to present this simplified version is because the skeleton of the more general proof is exactly the same, but we just need to do extra work for each of these three ingredients. Okay, so I'm actually not going to tell you anything about 2 and 3, but I did want to tell you about how we accommodate approximation, because that technique is just a separate contribution to convex optimization that has nothing to do specifically with mechanism design. Okay. So for approximation, remember that I told you about this equivalence of separation and optimization that says that if you can optimize linear functions over a convex region, you can get a separation oracle for that same region. Now, a very reasonable question to ask is what happens if you just start with an algorithm that approximately maximizes linear functions? Okay, you can plug it into the same reduction. What will happen? Well, the answer is you will get something, and what we call it is a weird separation oracle. So we call it that because it is an algorithm that sometimes says yes, and it sometimes outputs hyperplanes. So it looks like a separation oracle. But it may do this very weird thing, which is that it may accept 2 points and reject all of their convex combinations. So here's a picture of what I mean. Is that maybe the region of points you accept has this like funny shape, and maybe you choose to accept both of these black points. But maybe you reject this red point, and as you reject the red point, you actually output a hyperplane that separates these 2 black points you accepted from the rest of the region you accepted. So this is a very weird thing, and it's unclear that you can do any kind of meaningful convex optimization with an object with this behavior. Okay. But what we show anyway is that despite this, if you can approximately optimize linear functions over any convex region, then you can get a meaningful notion of an approximate separation oracle for that same region. So what do I mean by meaningful notion? I mean that if you use this approximate separation oracle within the ellipsoid algorithm, what you will find is an approximately optimal algorithm for optimizing linear functions. Okay? And really proving this involves understanding the behavior of the ellipsoid algorithm over a non-convex region. Okay? Because essentially that's what you're working with. So with that, so now that's all I'm going to say about the main result, which is that we can find and implement a mechanism that approximately optimizes any objective for arbitrary agents in poly time, as long as you have black box access to an approximately optimal algorithm for that same objective plus welfare. Okay? So to wrap up, we started with this question posed in a seminal paper of Nissan and Ronin, which is how much more difficult are optimization problems on strategic input versus honest input. We studied it via this major open question, which is for what optimization problems is there a reduction from mechanism to algorithm design? So what I showed you in this talk is that for all objectives in a Bayesian setting, this reduction exists, as long as you perturb your objective by adding welfare. Okay, and just to remind you how I like to think of this is it says that transitioning from honest to strategic input computationally is no more difficult than adding welfare to your objective. Okay, and also we studied this important question left open by Meyerson, where he showed that in single-dimensional settings, the revenue optimal auction is a welfare maximizer. And this major open question was, what does a revenue optimal auction look like beyond single-dimensional settings? Okay, so what we showed is that no matter what the bidders' types are, the revenue optimal auction is a distribution over welfare maximizers on these virtual bids. So we definitely don't know nearly as much structure as Meyerson did in single-dimensional settings, but we do at least know something. Okay, and just to recap, like we said, the main technical contribution was we extended this equivalence of separation and optimization framework, and we did so by accommodating sampling error and traditional approximation. And I didn't tell you about how we accommodate bi-criterion approximations, but we did that too, and that's what enabled the result for make-span minimization. Okay, I also told you earlier that this reduction is tight for revenue, and so how you can think of that is that says that maximizing revenue is exactly as hard as optimizing welfare on virtual bids in this Bayesian setting. And second, I told you that we now know that it's NP hard to optimize revenue for one submodular bidder within any polynomial factor. And this is the first hardness of approximation result for revenue maximization. Okay. And then last in this talk, I also told you earlier that we got a 2 approximation for truthful scheduling on unrelated machines. And this is cool for 2 reasons. The first is that it matches a guarantee of the best known algorithm. So even if we didn't care about truthfulness, we don't know any algorithms that get better than a 2 approximation for this problem. And second, even if you don't care about black box reductions, this is the first constant factor approximation at all for this problem in unrestricted Bayesian settings. Okay, so that's all I'm going to say about the main result. And I was very quickly going to talk, actually maybe like 5 minutes, I was going to talk about some other work that I've done. And just to remind you, I would describe my work as addressing novel challenges in algorithm design, and specifically challenges that can't be overcome by just doing traditional algorithm design better. Okay. So the first problem I want to talk about is profit inequalities. And this is a fundamental problem in applied probability and optimal stopping. And here you're given as offline input a sequence of distributions. And one at a time, a random variable is sampled from each distribution. And you have to decide immediately, do you accept or reject? If you accept, then you keep this reward and you don't see anything else. The game stops. If you reject it, then you throw it away forever and you get to see the rest of the game. Okay, and so this question studies how well can a gambler do who doesn't know the future compared to a prophet who does know the future. Okay, and there's a seminal result by Krengel and Sucheston and also Garling that says that there is a strategy for the gambler guaranteeing him half the expected reward of the prophet in expectation. Okay, and this is the best possible. So what do? Is we want to study the problem where the gambler has multiple choices. So what I mean by that is that instead of the game stopping when you accept something, you add it to this accepted set. And this accepted set must at all times be feasible. So there are some feasibility constraints. Okay, so the idea is that accepting something now doesn't stop the game, but it does limit the choices that you're allowed to make in the future. Okay. So what we're able to show with Bobby Kleinberg is that whenever the feasibility constraints are a matroid, there is a strategy for the gambler guaranteeing half of the profit's reward in expectation, and this is the best possible because it was the best possible even when the gambler was only making one choice. Okay, and in follow-up work also with Pablo Azar, we showed that there are asymptotically optimal strategies for the gambler that just require one sample from each distribution. So even if you don't know these distributions outright, you just get one sample from it, you can still do something interesting. Okay. So the second thing I'm going to talk about is what I'll call auctions for everyday people. And the motivation for this is that I think that the mechanisms I just described to you, I do believe that they're manageable. And by that I mean I do believe that if the FCC wanted to, they could run this mechanism as a spectrum auction. Okay? But I do not think that these mechanisms are simple in the sense that I do not think that I could run this mechanism to sell my old Pokemon cards. Okay? So there is some bad news on this front, which is that we know that even in ridiculously simple settings, the unique optimal mechanism is sometimes very complicated. Okay. Now there is some good news, which is that it doesn't rule out simple and approximately optimal mechanisms. Okay, so let's go back to the model of one additive buyer in one seller, and there are n items. The buyer has a value for each item that's sampled independently. Now, one very simple way to sell the items is you just sell them separately. So I put a price on every item, and I say you can buy whatever items you want. So think of this as like any time you've ever bought something, like at a grocery store, it was by this. Okay? Another simple way to sell the items is I just bundle them all together, and I put one price that says, if you pay me this price, you can take everything, or you can pay me nothing and take nothing. So think of this as like when you go to a buffet. You pay one price, you can take whatever you want. Okay? Now there's still some bad news, which is that a recent paper by Hart and Nissan showed that there exist instances where selling separately is a bad idea, and there also exist instances where selling everything together is a really bad idea. Okay? But in joint work with Moshe Babayev, Nicole Morlika, and Brendan Lucier, we showed that for every instance, either selling separately or selling together is a good idea, and that it gets you a constant approximation to the optimal revenue. Okay, so as a corollary of this means that if you sold anything on eBay recently, probably you did it in a way that is provably approximately optimal. Okay. Now the last thing I'm going to talk about is some more applied work that I've been getting into recently, but I do want to say it is ongoing work. It's not like we have good results yet. And so the first application is to real-world auctions, and the motivation for this is that I really do believe that understanding the mathematical structure of auctions is important, but an equally important question is, should real sellers change the way that they sell goods? Okay, and so the goal of this project is, first, we're trying to reverse engineer what does a real-world value distribution look like, and we're trying to use data from past eBay auctions. And once we have this, we want to try and study the performance of existing auctions versus what our optimal auctions predict you should be able to do. Okay, and then the last thing I'm working on is peer grading in massive online open courses. And so the idea here is that these classes are enormous. Sometimes they have over 100,000 students. How is a professor supposed to grade 150,000 assignments in a meaningful way? Okay, so one solution that's inherently scalable is maybe you can have the students grade each other. Okay, and there's actually evidence that suggests that students are capable of grading each other accurately. But the issue is, how do you encourage a student to actually do a good job? Okay, so inherently this is a game theory question. And so what we're trying to do is, first, we want to try and model how do students behave in a MOOC. When you ask them to grade something, what will they do? And once we model this, we want to try and use game theory to develop a sound peer grading scheme. Okay, so that's everything I have. Thanks a lot for coming and listening. Time for maybe one question.
You mentioned you have some other descriptions for the problem that it cannot be converted to the reduced form.
Yes.
Not sure I got that out.
Sure. Yeah. Sure. So right. So I didn't intend to talk about it, but I would say another way to describe a mechanism is maybe I can just list for every pair of types that you might have, what's your value if your real type is this, but you choose to say this instead. So that is still a low-dimensional description. It's polynomial in the input size. And this is now enough information. Does that make sense? So we're not using the reduced form anymore. It doesn't make sense to talk about items. It doesn't make sense to say that bidders are additive. But this is enough information. If I describe a mechanism in this way, then kind of no matter what crazy valuations you might have, this is enough information for you to determine if the mechanism is truthful or not.
Right.
Does that make sense?
What about if that you have a space explosion problem with such description?
Right. So it turns out that you can. So the space is bigger, the dimension is larger, but it's still small enough that it's polynomial in the size of the input. Right. And we can still optimize. We can still go through the same skeleton and use the same approach.
Yeah, but how do you that still polynomial?
So it's
How
still
do you guarantee
polynomial
that's
because
still polynomial?
yeah, sure. So I just have a variable for every pair of types. So if you have, so I think of the input as, you give me your type space, and now for every pair of types in your type space, I have a number. And that number is what is your value if your real type is X, but you choose to say Y instead. Right? So even if your types are very complicated, and maybe it's a very hard computational problem for me to figure out what is your value if your real type is X, but you say Y, the number of variables I need is still polynomial in the type space.
It's okay. We can
Is that-
talk
okay,
offline.
sure.
Okay.
Yeah.
Yeah.
Thank you.
Okay, thanks.